Hello and welcome to Morehouse's Math Menagerie. Today we're going to talk about least squares regression lines. But before we begin, I thought I'd offer you this fun fact. In America, 3 out of 4 people make up 75% of the population. We're going to be using data that comes from individuals who had their 40-yard sprint time recorded in seconds and their long jump distance in feet recorded. You may want to pause the video here and put this data into your calculator. List 1 should be the sprint times and list 2 should be the jump distance. Here is a scatter plot of the data on a TI-84 calculator. You can notice it has a linear pattern to it, and we've talked previously about calculating the correlation coefficient R that would help describe the strength of this linear association. But once we've established that data has a linear relationship, we would want to use a line to model that data. The line could help us understand the relationship better. It could also help us predict response variable values for given explanatory variable values. We could plug in a sprint time and help predict how far they could jump. This model is called a least squares regression line, or an LSRL. We'll talk later about why it has this name, but for now we're just going to look at the equation of the line. The equation of our line will look different than what you've seen in previous algebra classes. Here on the left we have a y hat, that's how you pronounce that, y hat equals a plus bx. The y has a hat on it because that y is a predicted value, not an actual value of the y variable or the response variable. Sometimes you'll see this equation, instead of using a and b, they'll use a b sub 0, referred to as b naught, and then a b sub 1. So you could see the equation written in either of these formats. In this equation, A stands for the y-intercept and B stands for the slope of our line. Now, what this looks like in practice is jump time with a hat over it equals 34.5632 minus 3.812 times sprint time. Now, that should say jump distance instead of jump time. That's my bad for that typo. I apologize. We'll talk about how to get these numbers later, but for now, just know this is the equation that models the relationship between our sprinting times and our jumping distance. Now that we know what the equation is, it's important that we understand what the slope and the y-intercept actually mean for this problem. So the first thing we're going to do is we're going to interpret the slope. You'll recall that slope is the change in the vertical direction on a graph divided by the change in the horizontal direction. So we could say, on average, for every 1 second faster a person runs the 40-yard sprint time, they will jump 3.812 feet further. We could also say that on average, for every 1 second longer it takes a person to run the 40-yard sprint time, they will jump 3.812 feet less. It is important that you use on average when you're interpreting slope and y-intercept, because this is a model, not a precise prediction. On the graph, the y-intercept is the point where the line crosses the y-axis. So here we could say, on average, a person who runs the 40-yard sprint in 0 seconds will jump 34.5632 feet. That doesn't make a lot of sense in application because nobody's going to run 40 yards in 0 seconds. However, that is still the interpretation of the y-intercept. You will find that on many of the data sets that we work with, the y-intercept doesn't make sense in context. That doesn't mean it's still not a valid interpretation. And note again, I use the term on average to clarify that this is a prediction and not an exact value. Using our equation, we could predict values for individuals that were not in our data set. For instance, we could ask the question, how far would we predict a person would jump if they ran the 40-yard sprint in 6.25 seconds? Using our equation, we can plug in that 6.25 for the sprint time, solve the equation, and we would predict then that this person would jump 10.7382 feet. Another example here If we had someone who ran the 40-yard sprint time in 5.75 seconds, we could ask how far would we expect them to jump. Again, plugging that value into sprint time, 5.75 there, we could solve this and say we would predict them to jump 12.6442 feet. Take a second and practice one of these on your own. We have to be careful when we are predicting values using a least squares regression line. If you get too far away from the interval of x values or the interval of the explanatory variables in your data set, the predictions become inaccurate. This is called extrapolating. You can extrapolate a little bit outside of the x values, but you don't want to go very far. For instance, the sprint times in our data set go from a minimum of 5.05 seconds to a maximum of 7.25 seconds. If we wanted to try to predict how far someone could jump if they ran the 40-yard sprint time in 11 seconds, you'll notice that 11 seconds is really far outside the range of sprint times in our data set. Plugging that 11 seconds into our model, we would predict that they would jump negative 7.3688 feet. Well, it doesn't make sense that someone would jump negative feet. So you can see here, our model is mostly useful within the range of data values that we were given. If we go outside of that and start extrapolating, things can get pretty inaccurate. Okay, a couple of vocabulary terms for you. We've used the term outlier before when we were dealing with a single data set. In a data set that includes bivariate data, that means 2 data values for each individual, an outlier is a data point that's within the range of the explanatory values, but is far away from the least squares regression line. So you can see here, this red dot is an outlier because it's within the range of x values. However, it's really far away from our least squares regression line. A high leverage point is a data point that is not in the range of explanatory values, but is close to the least squares regression line. The red dot on this graph you can see is very far away from the rest of our data in the horizontal direction, but it still falls within the general linear pattern. So let's talk about how we find the least squares regression line equation on a TI-84 calculator. The first step you want to do, and I mentioned this at the beginning of the video, is to put your data in list 1 and list 2. The explanatory variable, or x value, should go into list 1, and the response variable, or the y value, should go into list 2. Once you've done that, you're going to go stat calculator and then down to number 8. Once you've done that, you're going to hit stat calc, and then you go over. Once you have your data in the calculator, once you've done that, you want to hit stat and go over to the right to calc, and then down to number 8, ln reg a plus bx. You will note that number 4 is also a ln reg, but it doesn't use the same format that we use here in AP statistics. So I would encourage you to use number 8, which keeps consistency with a being the y-intercept and b being the slope. After selecting that ln reg a plus bx, make sure your x list is your list 1, your y list is list 2. You want to keep your frequency list blank and go ahead and hit calculate. Here's the output for the ln reg. We've done this before to get our correlation coefficient, but now we know that a is our y-intercept and b is our slope. Why don't you practice finding the least squares regression line equation using this data for gestation periods and longevity for various animals? Here is the equation that you should have gotten on the previous slide. Use this to answer the following questions. I will leave you now with this quote from John Ruskin. I hope you enjoyed the video. Have a great day.